Okay, so my name is Aivars. Originally, I wanted to give this talk a title, something like with CSI, but then it would give impression that I'm working in crime, so which is not the case. So I work with fintechs. I spent a huge part of my career building software in C++ on different kind of Unixes, and the main thing there was that we delivered the software to the clients and clients were running it, but we didn't have the access to the client system. So whenever something went wrong, we had to figure it out through log files or to give customers some commands to execute, then get back the feedback and figure out what is happening there. So we didn't have like access with debugger like developers normally do. So now I work for eBay. Situation is technologically, it's a bit different, but we still do not have access to production system because of regulations in the finance and so on. And I work also on a lot of private projects. I also help if somebody has a trouble with their systems, I can help and figure out what's happening. So that is because I have to give this disclaimer. So I will show a lot of issues. It doesn't mean that the companies I associate with had all those issues and they are struggling daily. It's just that I have this selection bias. So I go where there are problems and try to solve them. And also, if you get, I don't know, HTTP 500, well, you might skip it and whatever happened, as long as it works now, I'm the person who sees 500 and I have to know why it happened. So that's why I get into a lot of these investigations. And I will start with the simple things. Okay, so first, if you are working with Linux, there's, I suggest buying this book from Brendan Gregg. He talks mostly about the performance issues, but he lists a lot of tools that can be used and where to use it and how to analyze all of that. And it also helps a lot when you troubleshoot things. So I will use some of the tools listed here and some of the tools that are not listed here. Then let's start with the simple things. So the process file system. And since we have time, and I gave a talk about this a week ago in SRE Days London. So the interesting thing is that we have association with Unix. Everything is a file, right? So that's what they say in Unix, everything is a file. Turns out that the process file system was introduced only in Unix version 8, around 1984. So quite late in the Unix history, they got the processes as a files. And there's the manual page for Linux because every Unix does it differently. So, but the most useful things you can find there is, so for Python, I would say this is for the process ID, you look at the CVD. So it's the current working directory, and this is because sometimes your application looks up files with a relative path, and you must know from which path it starts. The next super interesting and useful thing, even now with the cloud, is that to check out the environment of the process. And so because right now in the cloud, the way how you pass secrets into your application is through environment variables. And then you start your application through some layers of shell scripts that sometimes they lose the variables, sometimes they come from environment, sometimes they come from files, sometimes they get overwritten by values, let's say from the vault and so on. And this /environment is file, it's using this C string conventions. It means that every string is terminated by a 0 character, 0 byte. And if you want to print it on the screen, I typically pipe this through this translation utility, which translates binary zeros into new lines. And so then it prints it nicely, and I can see what kind of database passwords, database host, and what else secrets you have for your application. Another one I find useful because it's tricky to get right is the limits file. For Python applications, mostly what's interesting is the maximum number of open files. So on Linux, by default, it's 1024, and applications typically run into these limits, especially if they are handling requests from multiple clients. And and what's interesting, since in Unix everything is a file, your connections are also fall under these open files limits. So, and you can go through each individual file descriptor. Those are in the FD folder on the pros file system, and you get the file descriptor number, and then you can see what it points to. Some of those are to the terminals, some of those are linked to the sockets, so outside or outgoing or incoming connections. Some of those are files, and some are like another interesting stuff for event polling. Now the question is, how do you know if you have hit the limit on the file descriptors? And the way Unix is built, it's interesting because we talk about maximum number of open files. It's actually the highest file descriptor. And then there's this convention that the file descriptor has to be assigned the lowest number that is not used yet, so we get a similar effect. But in the Unix kernels, typically those file descriptors are stored in an array, and what we get as a file descriptor is just an index into that array. And so if you are building some networking application and you have to handle multiple sockets, the right structure for that is an array, so do not store it in map, because the kernel will take care of that. Those are put to that the number is as low as possible, and it doesn't go over the limit that is set here on the limits. So then how do you know if you are hitting the limits or not? The best way is just to look at the largest file descriptor, and typically, so here it's 39, it's highly unlikely it's hitting the limit. If you see it in 8 or 900s, then in that case it might be hitting limits, especially in like a highly loaded application that is processing a lot of short requests. But this FD folder comes in handy in other cases as well. And the topic is restoring deleted log files. So here I have a simple Python application that opened the log file and it keeps writing something to the log file over the time. And it's running in the background. And then, so I check out that this log file has grown to like almost 10 gigabytes. It's taking a lot of space, so I want to delete it. If I just delete the file, then the disk space is not released. It's still 72% used. So here I did this intentionally just to free up some disk space, but this happens a lot in production where there are application logs that are written to the disk, and then sometimes this log rotation is set up incorrectly, or it gets into weird timing and a new log file is created, but it stays empty, and everything is written to this log file that is already deleted. So first, why the disk space wasn't freed? So this goes back again to old Unix history. So Unix didn't implement syscall that does the removal of the files. They implemented the syscall that is called unlink. So what it does, it essentially removes the file name out of the index, but it doesn't remove the file data from the disk. Instead, it keeps the kind of like counter or reference counter, how many processes have opened this file, and once all the processes close the file, so the reference counter drops to 0, and there's no file name entry for the file, only then Unix removes the file completely. So until some process is using the file, the content still stays there on the disk. So the answer, what to do with, if you want to get rid of the disk space, you have to restart the process. But the question is, how do you find out which process? So for my example, I know the process ID. So if I look at the FD folder, I see that the file descriptor number 3 points to this large log file, and it has this node that it says it's deleted. So I know, or if I don't know the process, I like to do this. I simply go through all processes. I look at the file descriptors and check which ones have been deleted. And there I can find out the process ID. So if I need to clean up the space, then I would kill this process. More realistically, it's the case where something important is being written to these log files, and we still have to investigate what the application is doing. In that case, you can use these file descriptors instead of the actual files. So like, for example, I can tail this file descriptor number 3, and I can see logs being written in the real time. So I can check what application is doing before killing it and getting a clean log file. Or sometimes I just copy the whole content of the log file to some new file, and then I kill the process. So that's how you restore deleted log files. Then another interesting question you can answer using process file system is which actual process is using this file. So I'm interested in which processes are creating this Lua snip file. And then I do a similar grep on the file listings, and I find the process IDs. I can check what are those process IDs and why are they using this Lua snip file. So it's something to do with NVim, as you might imagine. And there's a Linux utility called fuser, which does the same, but it has to be installed from a separate package. So oftentimes it's not available. So this works all the time. And while we're on the topic, so this is not related to the process file system, there's also this tool called inotify-wait, for which you can change all modifications to the file system. So you can check when the files are being created, when somebody opens a file, when somebody changes, let's say, file permissions, when somebody modifies file, closes it, moves, deletes, and so on. And sometimes it's, for example, there's this, when Nginx forwards data to some WSGI process, and if the data is too large, then it creates temporary file on a disk and then passes this file. And if you know the folder, you can use tool like this to monitor how often that happens, how often it writes something to the disk. The worst the problem with this is it doesn't give you information about the process, who does it, which ones do write these files. So for that you need some other tools, but that's kind of completely different topic. So now tracing. So normally, as a developer, if you have problems, you typically would launch a debugger. So, but this was not an option for me for many years. So instead, we relied on tracers. So there's Truss and similar tools for other operating systems. For Linux, its most popular is strace. And how it works, it actually attaches to the process, and then it prints out whatever the process is doing. And it gives you system calls, just the system calls. So it doesn't give you complete information, but using this tool, and if you learn it well, you can debug any process. Is it written in Python? Is it written in Java? Whatever. I don't care. I don't care what kind of new libraries and new semantics this application is using. Is it clean code? Is it garbage code? I just use this and I see what it's doing. The greatest thing of it all is that it doesn't require root access. So other tools like perf and bpf trace, they require root access. This one, you can debug your own, processes of the same user without any limitations. And it kind of also gives the trust to people who, you ask some people to execute some strange command and expect them to send you the output. and if it requires root, so most admins won't do that, but with this, it's fine. One also very nice property of that is that if your system doesn't have it and you don't have root access, you can still install it without root access. So, and I have done it multiple times. I have done it inside Kubernetes pods. So what you do is you download these two packages, so strace and libunwind. You unpack them, and then you just specify the path to this libunwind library, and you can run the strace just like that. So it sounds, I mean, it's not that hard. You can do it. Then what is the basic usage? So you can run it on either on some Linux commands or attached to existing process. So the typical like parameters I use is this -f. It means if your application is multi-threaded, it will keep track of all threads. If it starts new processes, it will keep track of these new processes. Then this -ttt, so it just prints very, very detailed timestamps, so I can get timing information. -o, it just sends output to a file. And then this -s, so for all function calls, there's a limit of how much data it prints by default. So if you are sending, let's say, 1 kilobyte of data, then by default it will be, you will see only the first, I don't know, let's say 80 bytes. But you can increase that size and to kind of capture the whole load of work, I mean, the whole block of information. There are some other flags like -xx, it prints all the strings in hex, so it's easier to process after that with some tools. And there's -e, which allows to filter on specific syscalls, so you get a cleaner output. And then strace by default prints everything to error output, so you have to do this forwarding to be able to use with grep. Okay, so here's example with strace from one of the processes. So just to give a visual, so on the second line it sends send2, and if you look closely into the bytes, you see that it says select distinct on loan something. And then on the fourth line, there's receiving, so it kind of receives some data, and there's request ID and things like that. So you can imagine that it returns query results. And typically this is happening really fast, so it just scrolls down the screen. If you look at how it's implemented, and if you have like slower syscalls, then it looks like this. So typically each line is split into two parts. There's the entering part, which is printed when the syscall starts, and then there's exiting part, which is printed after it ends. So here we see that the syscall is made, but it hasn't returned yet. So once it's returning, you will get this -1, so the result of this syscall. And there's the receive from, and it typically just prints the socket on which it tries to read. And once it's received some data or got an error, then it prints the remaining part saying that, okay, now I received this data, and so on. And yeah, and this is very nice because if some of these system calls are taking longer time, you can see that, oh, okay, this has entered and it has not yet exited, so it means it's hanging because of some reason. A small cheat sheet. So I don't know what's your background, but so I used to do low-level programming. So most of this is familiar, but there are a couple of most important ones. So things starting with epoll, select, p-select, poll. So what the application is doing, it's doing some kind of multiplexing. So it's typically handling multiple incoming connections on multiple outgoing connections, or the other option is that it's implementing some timeout waiting for, let's say, user input or request to arrive. And this is fine if you see your application is kind of entering these functions and not exiting. That's the expected behavior. Then there are reading data from the outside. So it's typically read, receive from, and also accept. So accept call is used to accept new incoming connections. And so these you often also see that they are kind of waiting in this entering part. There might be good reasons or not. So there are other, when you send data, so it's write to and send to, so those typically do not block. It's very hard to get them to be stuck. There's also the connect call, which is waiting to connect, and this only happens if the application does the connection without timeout, and it's actually pretty bad. So no application should do just a bare connect. It should always have the connect timeout. And if you have connect timeout, you would see that connect returns immediately, and then the application is stuck into some select or poll or epoll, waiting for the actual connection to happen. There's wait for, which typically waits for child process terminations, and there are futex, something which are typical when you have some waiting on a lock. There's also this nice link I found about Linux syscall table. So what's nice about it, it lists all syscalls, it lists all syscall numbers, because inside the kernel, syscalls are recognized by the numeric ID. And it also points you directly to the manual pages of each of those syscalls. So it's really, really nice to see and read details about what this exact syscall did. Another really important part about strace is whenever you attach to a process, and especially if the process has multiple threads, the first lines will be reporting status of all threads of the process. So when I attached to this process, it printed this, and then it kept printing more stuff about application going on. However, if you pay close attention to the first line, so it says it has 3 threads. So then the first PID, it's waiting on some futex. So, and then second line is waiting on some futex as well. So, and I don't know if you can see it, but those futexes have different addresses. So it means it's not waiting on the same futex. So in this case, it's classical deadlock. So 2 threads have deadlocked, and the third one is working fine and doing stuff. So pay attention to the first lines of the output. Okay, now story time. So what happened is that the system became slow, unresponsive. So, well, I mean, users tell that our system doesn't work at all. So it was a jungle app. Luckily, so I was able to connect to the server. And then I started to look what's happening. So not much information in the log files. I found the process ID of one of these UWSGI servers, UWSGI processes, and started to look at what it's doing. And they were doing something like this. So they were doing connect, and they didn't print the exiting part. I looked into other ones, they were doing connect, and again, no exiting part, and so on. So it means that the connection to the outside world is somehow, the connections are not being made. And the most interesting part, so we have Sentry disk here. So what happened was that the application failed to connect to external resources. After some time, it kind of got an error that the connection failed. And then because of this failure, the application tried to report it to Sentry, but Sentry is external resource. And then it stopped again, waiting to connect to Sentry. And yeah, and the reason was that the Python code was not implementing connect timeouts. So that's why each connect was like taking a really, really long time. And it was a network issue, so we called data center, and they started investigating, and in total, something about 45 minutes, the system was back up again. What happened in the data center, I don't know. They messed something with the outgoing connections, that's as far as I know. But yeah, so at least, yeah, this got solved out. Another story time. So this was, again, this time the problem was that the application is running a lot of background processes, and they are queuing up, and the things that should have been done on time, they do not get done on time. So we connected to the server, looked at the CPU load, it was more or less okay. I mean, not okay, but typical for that server. However, it had unusually high I/O load, so it was doing something on the disks. So at that time, I think I used Nmon. So that's a really, really old monitoring tool that shows the disk utilization percentage. If you do not have Nmon, it's also IOStat. If you run it with -X, the last column is the utilization percentage, and the utilization was something like 80% of the whole disk. And yeah, once again, so try to find the process ID of one of the background tasks to see what it's doing, attach to it, and then it's doing something like this. So it's statting files. So basically, this is a system call to check if the file exists or what size it is. And it was doing the same, a lot of these calls for the kind of same similar patterns, something saying that /storage/ something. So what was happening? The application, so it had kind of custom file field. So it wrapped around the standard Django file field and then did some custom logic, and the logic was there to check whether this specific file name exists in the active folder or in one of backup folders. So it was trying to find where this file is. And kind of what triggered that was that this background task, for some reason, it was getting not loading 100 objects, it was loading, let's say, 200, 300, which kind of it's not good, but the question is why the I/O? And I/O is a bit tricky. So there are typically two things they measure for devices. So one is called I/O operations per second and then throughput. And throughput typically is calculated like I/O operations per second times whatever size we write to the disk. Why this is tricky? Because a lot of, companies, individuals, they typically give you throughput, and they do not tell for which I/O size they did this. So let's just quickly skip over it. So this might be different for reads or writes. So I typically prefer to look at the writes, because if I know writes have this kind of throughput in I/O operations, then I can estimate that reads are probably better or 2 times better than writes. Also sequential versus random. So random is very hard to measure in a reliable way, so I prefer to look at the sequential and then estimate whatever else is happening. So, and why this throughput is kind of sketchy measurement is because typically applications work with different sizes. So if you do something on a Linux file system, Linux typically works with 8 kilobyte blocks. If we work with databases, so default size is 8 kilobyte blocks, and this is like the unit that is being written to or read to disk. And what they do for throughput, they just write like large blobs like videos, audio files, and then they show, oh, this is the great throughput number, but they do not tell what are the I/O ops. And then there are like different things inside the kernel. The kernel manages to sometimes merge some of those writes, so it's a lot of different layers of caching and complication. But where I'm going to is that so the company had migrated to new servers, and with new expensive enterprise level, how it's storage area network. So it's disk device that is available over the network. It was just bought, so it's new and shiny. Numbers look great on the paper. However, if you do so these are the metrics I have preserved. So this is on a database block sizes. So for Linux file system, I would do 4K, but it's still, you see the difference. So the new server with new shiny hardware got only 27 megabytes per second, and the old Hetzner machine that was running at least, I don't know, for at least 2 or 3 years, it was pushing more than 300. So it's 12 times the difference. And yeah, so eventually they managed to get the Sun performance to something like 54 megabytes per second, but that's as far as it goes. So with these cloud virtual machines and so on, do not just take their word for it that it's fast. Do your own comparisons, compare it with your local laptop. So my laptop, my 5-year-old laptop, is doing better numbers than that expensive Sun. Okay, let's talk about networks. So the most common issue I have with networks is that so we are doing some kind of integration between two companies, and typically on each company's side they have to open the connections to go through in a firewall. The other company has to do that and configure routers, and then when you start testing it, the application can't connect, and you tell, oh well, there should be a network problem, and then both sides say that, oh, on our side it's fine, it's your application problem, and then you as an application developer have to figure out what's wrong with the network without using any network tools. So if you Google, there's a lot of, like, typical, what they suggest is to use ping and traceroute. However, in any like serious organization, they have cut off ICMP traffic and also UDP. So you do not have these packets that are used by the tools to test the network. So what to do next? Luckily, there's a program called TCP traceroute. So it works like a traceroute, but it uses TCP connections. So instead of specifying the host IP, you just you have to also specify the port. So it tries to establish connection to the port, and then it shows you how the packets got there. So this is kind of a typical output. So I try to change some of the IPs so I don't expose too much information. But the idea is that it gives you the same output. So every step, every router, the packets go through. And also, so there's typically some stars in the middle, and then you have some more lines in the incoming side, I mean the target side. And then you show this output to the networking guys, and then they say, oh yeah, but why the packets are going out through this router? They should go through a different router, and therefore they get different IP. So then you show this to them, and then they figure out where they went wrong. If not on the first time, on the second time they will fix it. Another interesting thing is, so this is netstat is common on many Unixes, but there are some Linux-specific flags on it. So here, the most interesting probably is that -p asks to print the processes, and -a says to print out. So the term is listening and non-listening connections. So basically, you want to see every outgoing connection and every incoming connection, and as well sockets, I mean servers which are listening on some ports. And then I think this is Linux specific, this -o, it also prints network timers. So it's not very readable, but I will share the slides. The idea is that at first you get listening sockets, so you see what kind of servers you have running on your machine, and then it prints all the connections. And so these connections are from one of my laptops to, I don't know, wherever, but there are IP addresses, host names, so it's Chrome. So I have a lot of tabs in Chrome, as you can see. And the last column are the timers. And the most interesting numbers are the last two zeros, here zeros. So one of them is retransmission count. So if you have an issue with a network where packets have to be retransmitted, you will have some number here, there, and also there's I think, I don't remember which number, but one of them is also the keep alive counter. So that's, okay, time for story. Okay, so this one I like. So about slow Kafka producers. So we were testing a new service that is using Kafka, and this is what kind of was first like really serious project because it was taking huge amounts of CDC events. So everything so on the first deployment, it had to read through, I would say, millions of events for all previous changes, and then it would get only the new events that have happened after that. So we had to consume huge amount of events, and in the end, the process takes that, it does some transformations and produces new events. However, it was working at around 20 events per second. So the initial deployment would take weeks. But I mean, people were like, okay, so it's just the first time, so it won't be a huge mess. The important thing is that once this is done, it will work sufficiently good and we can scale it because it's Kafka, right? But yeah, I had intuition that something is not there, so I went to investigate. So first, I turned on logs for the Kafka library, and so it's hard to make out, but basically, so the producer response came in 33 milliseconds. So I started to check what's the networking conditions. So I did a trace route to one of the brokers, so it was fine around 1 millisecond. So then the question is where the time goes. So this is one of the times I had to install strace into Kubernetes pod without any privileges. So there's a lot of output, but so which line it is? So it's line number 5 from the top. It does poll, so it waits for some event on the network, and then it resumes after some time. And if you look at the difference, it's something like 47 or 48 milliseconds because that was the timing. And at that part, so I saw that, okay, it spent that much time on the network. And there are just some things you have to know. So this is actually a title of one article. I really like it. So it's always TCP no delay. So whenever you see numbers around 40 milliseconds or a bit more, or transactions per count or requests per second, something around 20, 25 events per second. So this is actually a magic number. And especially in the network applications. And oftentimes people do a lot of optimizations and they can't beat these numbers. What's happening in reality is that there's infamous interaction between Nagel's algorithm and delay DAX. So these are two network algorithms that are implemented in every operating system. And this TCP no delay, it turns off the Nagel algorithm. Although me personally, I think the Nagel algorithm is kind of more, it makes more sense to me. But again, the problem is caused by interaction between those two algorithms. And it gives you like 40 milliseconds latency. So the first link is the article explaining it. So you will get the slides, you will get the links. So what's interesting, I have opened the ticket with Confluent for Kafka library to turn this TCP no delay on by default, because it's not doing that by default, and it's still, I don't know, almost 2 years, little activity. And there's, writing this, I also found this nice article about pointing to exact place in the Linux kernel code where these 40 milliseconds come from. So yeah, so basically there's a way how you can turn on this no delay through some additional parameters, but it's a shame Kafka is not doing that by default. And there are other tickets asking to document this, but it's still no response. So another story, we have time. So it's about timeout issue, so the setup was that there was a Python HTTP server performing calculations. Depending on how much input it gets, it takes longer time or shorter time. And it does some pretty heavy calculations, so it's expected to be slow. There's a Scala HTTP client requesting the data. It's all running on Kubernetes. And the way it's implemented is that it does a single HTTP call, and then it just waits for a response, and sometimes it takes a minute to whatever minutes to get a response. So not the best way to implement it, but it is what it is. So I'm not going to judge the company, but I'm going to tell about them here at conference. And yeah, what was happening is that if you do small requests through this setup, well, it might take some minutes because, again, there's a heavy calculation, but it works. And at some point, by doing larger requests, you do not get a response, and after 2+ hours, it times out and it breaks. And the most interesting thing is, so we actually tested this from the Kubernetes pod, is that the curl, using this command line utility, it actually gets the response, gets it in a reasonable time, so looks fine. And the question is, what is curl doing differently? So I always like to use curl as a template for any good networking code. If you want to understand how to write good networking code, go there. So because what curl does, so when I do a request, so it first creates the socket. So it creates socket number 3. First thing it does, it says TCP no delay, the thing I talked in the previous issue. It does that by default. And then it also sets socket options about keep alive, keep idle, and keep interval. And do you know why it does so? Because, I mean, the Linux defaults are bad. So, I mean, I don't have any other words. So back in the days when we treated our servers like pets, so we used to tune these parameters on each individual server. Now you just get some EC2 instance or whatever node you get in Kubernetes, and you get the Linux defaults. So what it says is that, so the last number says that it will send the first keep alive packet only after the connection is idle for 2 hours. And then, so it will send the first packet. If it doesn't get response, after 75 seconds, it will send the second one, and then it will send another one after 75 seconds, and it will do so 9 times before deciding to declare this connection is dead. So these are actually reasonable numbers. And if you think, well, this is Scala issue and Java issue, we do not care about this, look at the requests. So URL lib in Python, if you do an strace on it. So one thing I have to applaud here for the URL lib, because it sets TCP no delay by default. Imagine some HTTP client in Python does this, and Kafka client of scalable, whatever streaming platform doesn't do that. Yeah, but it doesn't set those delays. And then again, so what is happening is that somewhere in between there's a firewall or gateway that is dropping the connections that have been inactive around 5 minutes. And as it drops the connection, client doesn't get the FIN packet. So the FIN packet is something a server sends back during like a graceful shutdown and announcing that the connection is going to close. So client doesn't receive it. And then, because the connections are dropped, server's response can't be delivered back to the client, so they are lost somewhere on the network. And then client starts sending keep alives after 2 hours. And then it takes some more minutes to realize that, oh, this connection is gone. So you might say that, oh, this HTTP approach of very long connections, this is not good, but we all have long-lived connections. So typical one is the database connection. And if you look at the, let's say, Postgres documentation, there are keep alive parameters that you should set for your connections. There's also kind of brute force approach. So if you do not care about if you do not want to go through the chain of libraries figuring out how to actually get to the socket and how to set these values in the socket, this is extremely good. So this is a library that will do it for you. You just preload it before loading your application, and then it will, whenever you create a socket, it will enforce these keep alive values on the socket. And this all works until you have some nice service mesh in your Kubernetes, because what they do is typically they act as a proxy, kind of layer 4 proxy. So they intercept connections from your application, and there, between application and proxy, you get keep alives, but then they establish connections on their own to the database, and there they use whatever the Linux defaults are, and so you lose the connections. And that's it. So, summary, there's a lot of interesting stuff in the process file system. strace it's my favorite tool. I use it to debug. Even instead of using a debugger for my own code, I just use strace on it. This TCP trace is nice. Keep in mind about 40 milliseconds. There are quite a lot of posts about companies realizing, oh, that this is a thing. And coming back to this, it should be well known. Set up TCP keep alive for long-lived connections. And the final point, if you have cloud computers, do test them, because oftentimes they say, well, you have to scale out, you have to buy more hardware, you have to rewrite your application in this way. Well, it might be that just your machine is like really, really bad. So that's it.
You said file descriptor count is the highest one which has been used. And is there any possibility for closed file descriptors to be reused?
Yes. Yeah, they are reused. So as soon as the file is closed, this descriptor is free and it will get assigned the next incoming connection.
So if you have 30 file descriptors and you close number 15, the next one you open will again be 15.
If everything up until that is filled up. Yeah. So if you have number 10 closed and you close number 50, the next comes in, will get number 10, not 50.
Always the lowest one.
When you close 15, but 10 has been closed before.
Yes.
Yeah.
You always get the lowest one.
Yeah.
Thank you.
Thanks for the presentation. I cannot wait to use strace to debug something waiting for me in Gmail. Wanted to ask for advice. So I think mostly you talk about like a backend when you have a cloud and you can connect like over SSH or something. Let's imagine that we have embedded device with Linux, right? So we don't have SSH access. If we want to troubleshoot something, like what can we use? Like what suggestions do you have for that?
Sorry, I don't have a recipe. So I haven't worked in that space, so I do not know. So I know that, my preference is to have like real hardware, then I can debug it. So with cloud servers, I kind of can get by, but for embedded, I don't know if it runs Linux. So the most important thing is it probably has this proc file system. You can at least get something. And depending on the architecture, you might be able to run strace. Because strace has limited support for architectures, you would have to check if it's...
It's possible to run strace, but you need to like connect to the device, right? So if it's deployed, if there is a user that uses this device, you don't have an access to it. Yeah. So it's like usually you just record whatever you can record, and then you retrieve it from the backend. But there are like disadvantages of that approach, and it does not give you that information that I think you can get with strace.
Yeah.
Thank you.
Good luck.